So let us start discussing about the helium atom. As I already told that this will be our example where we do not have any idea about the ground state energy and we want to figure out what should be the ground state energy or estimate for the ground state energy for the helium atom. This particular example is going to show us a few different nuances of application of variational methods in quantum mechanical problem. Among them are basically the fact that if we do not have any knowledge about the exact value of the eigenenergies, then how can we proceed to figure out what should be the upper bound on the ground state energy of a particular quantum mechanical system? Secondly, what we are going to do in the process of solving this problem is that at some point of time we are also going to apply perturbation theory techniques to figure out what actually are the or is the ground state energy, what estimate we get using perturbation theory techniques, and then we want to compare our result with whatever we have obtained using variational methods. And to our surprise, we will see that the variational method gives us much better estimate of the ground state energy of the helium atom compared to the first order perturbation theory results. Now, as we all know that one important application of quantum mechanics is to explain the structure of atoms. Here, in this particular example, we will be working with an atom which has 2 electrons. So this is the helium atom we are talking about, and the nucleus of this helium atom consists of 2 protons and 2 neutrons. So these are in the nucleus. Now, for all practical purposes, we can simply neglect the motion of the nucleus, that is, we assume it to be infinitely heavy, which is of course a good approximation to start with. So the picture that you may think of about this atom is something like this. We have this electrons, there are 2 electrons, say here one and here one. Of course this is a classical picture. And then we have the nucleus, which has the nucleus charge or nuclear charge of Z times E, where Z is the atomic number representing the number of protons. Then these are the radial vectors, and we should also remember that we can have interaction between the 2 electrons also in this picture. So of course this is a classical picture, but based on this classical picture we can actually write down the Hamiltonian for this system, which we will write as P1 square by twice mass of the electron minus Z times E square by 4 pi epsilon naught into 1 by R1 plus P2 squared divided by 2 times mass of the electron minus Z E square divided by 4 pi epsilon naught 1 by R2. And then we also have to, as I said, include the interaction between these 2 electrons. We will have a term like E square by 4 pi epsilon naught into 1 by R12, where R12 is the distance between the 2 electrons. Of course, we know that for helium, Z or the atomic number is of course equal to 2, but at the moment we will keep this as Z as most general expression, and there is a reason for that which will be clear when we go into the more details of this calculation. Now this Hamiltonian can also be written as in the position basis by writing the momentum operators as minus h slash square by 2 times me grad 1 square or the Laplacian 2 squared minus z times e square by 4 pi epsilon naught 1 by r1 plus 1 by r2 minus plus e square by 4 pi epsilon naught 1 by r12. Let us look at each term separately. This term basically is the total kinetic energy. This is basically the nucleus and the electron interaction term or the Coulomb potential. We have a charged object here at the center which has the charge of Z times E, and therefore the potential is basically Z times E into E, that means Z is square by 4 pi epsilon naught divided by the into 1 by R1. Similarly, this is R2. So these are the two terms, the standard Coulomb potentials, and this term basically tells us that there is this repulsion between the two electrons in orbit. Now, having written this Hamiltonian, we have to keep two things in mind. That firstly, we are assuming that the two electrons are basically distinguishable, and of course we know that electron being a fundamental particle, it's a fermion, they are not distinguishable, but we are assuming them to be distinguishable. However, there is a justification for that. As long as we are dealing with the ground state of the system consisting of two electrons, Pauli exclusion principle is always there to save us, and it says that their spins, these electron spins, must point in opposite directions, and thus we can treat them as effectively distinguishable. And we are also at this stage neglecting the spin orbit coupling for the moment. Spin orbit coupling we are not incorporating in this calculation. Having said this, we also have to note that atomic system looks like, this particular atomic system looks like slightly complicated than the hydrogen atom that we have solved exactly. However, you would be surprised to know that it cannot be solved exactly. Consequently, this system has been studied quite extensively by variational approach so as to draw some idea for more complex atoms. So there are several other methods that also have been used to know, but variational method or variational approach in this particular problem works like wonder. Now, at the moment, to start our calculation, let us ignore the interaction term to start with. So what we are doing here is that interaction term means the interaction between the electrons term. So this is the electron repulsion term or the potential. This is the nuclear electron attraction or attractive potential. So to start with, let us ignore the last term, that means ignore electron repulsive potential. then the system is equivalent to two hydrogen atoms. You look at this Hamiltonian, this is like one hydrogen atom, this is like another hydrogen atom, and for the time being we are not incorporating this term. So therefore you can immediately identify that the system or the Hamiltonian looks like a direct sum of two different hydrogen atoms. So now let us write down the ground state wave function for this, and the notation that we are going to use for that is that psi, let us put this 0 as the ground state to denote the ground state. We have R1, R2. This is equal to a product, because they are separable, N1, L1, M1, function of R1, and then psi 0, N2, L2, M2, R2. This R1, R2 might be a bad notation simply because this means that they depend on R1, theta 1, phi 1, the radial coordinate and the angular coordinates corresponding to the first electron. Similarly, this R2 here, it denotes that they depend on R2, theta 2, phi 2 corresponding to the second electron, although we have just discussed previously in the previous example when we discussed hydrogen atom that this is not, because this is the ground state wave function, it is not having any dependence on the angular part. Now we know exactly what these hydrogenic wave functions look like. I am calling it hydrogenic simply because of the presence of this Z factor here. So if this Z is equal to 1, then I would have said that we are dealing exactly with the hydrogen atom. But there is a multiplication by a constant Z at the moment. So we call these hydrogenic atoms. And we know the forms. That is very important in this case. The ground state hydrogenic wave functions, they have the form Z cube by pi A0 cube to the power half e to the minus Z R1 by A0, where of course we know that A0 is the Bohr radius and it has the expression 4 pi epsilon naught h bar square by mass of the electrons times E square. And similarly, we can also write down for the second one as Z cube by pi A0 cube to the power half e to the minus Z R2 by A0. And therefore, we can write down the total ground state wave function for the system as Z cube by pi A0 cube into e to the power minus Z R1 plus R2 divided by A0. So let me at this stage again number different equations. Let us call this 1, this 2, this together as equation number 3, and this is say 4. So this is the hydrogenic ground state wave function when there was no electron-electron interaction term. Now by construction, this equation number 4 is normalized. We have these factors sitting here. So by construction, this is normalized, and the ground state energy for the system in this case is basically the sum of the ground state energy of the two hydrogenic atoms that we have here. Remember that this term was absent to start with. Therefore, the ground state energy for the system will be the sum of the ground state energies of the two hydrogenic atoms separately in the absence of the mutual repulsion. So, keeping that in mind, let us calculate the expectation values of the potential as well as the kinetic energy, and we will calculate it just for one electron, and the second electron will also give us the same result, simply because at the moment we are just considering two hydrogenic atoms separately and we are not considering any interaction between the two electrons. So let us calculate. So suppose we are calculating the kinetic energy for the first electron. So what will be that? This will be a three-dimensional problem. So this is d3r1 psi 0 n1 l1 m1 r1, and then we have of course minus h slash square by 2 times me. We had del 1 squared and then psi n1 l1 m1 0. So that is what we need to evaluate. Now of course at the moment let us stop and think a little bit. What is this one? This is nothing but the volume measure in the spherical polar coordinate, and that is going to give us 4 pi r square or 4 pi r1 square dr1, because explicitly there is no theta phi dependence in the rest of this integral. So I can safely take this 4 pi out, and from here I can take the constants out, h slash square by 2 times me with a minus sign, and of course these si's, they have this factor of z cube by pi a0 cube, so that also should come out, z cube by pi a0 cube, and now we will have r1 square dr1, and psi 0 n1 l1 m1 is nothing but e to the minus z r1 by a0. We have to write down the Laplacian in the spherical polar coordinate, which has this form 1 by r1 square dd r1 r1 square dd r1, which will act on the wave function minus e to the minus z r1 by a0. There will be no dd theta and dd phi term because there is no theta phi dependence explicitly. So now this should give us minus 2 pi. I have to be very careful about all these factors now because they are very much important to obtain the final result, and this 2 gets cancelled and we have mass of the electrons time pi into a0 cube. Now this will have r1 square will get cancelled by this 1 by r1 square. We will have dr1 into we have e to the power minus z r1 by a0, but before that let us actually evaluate this part. This part will give us minus 2z r1 by a0 e to the power minus z r1 by a0, and then there will be a plus r1 squared z squared by a0 e to the minus z r1 by a0, and whole thing multiplied by e to the minus z r1 by a0. That is what we are going to get from this expression. So this, if I now write it more explicitly, we will have, in fact this pi gets cancelled, minus 2 h cross square z cube by m e a0 cube into minus 2z r1 by a0 plus z square r1 square by a0 in fact I think I have made a mistake here. There should be a factor of a0 squared here. Yes, and then e to the power minus 2z r1 by a0 dr1. Now at this stage we will use a standard result of integration, that from 0 to infinity x to the n e to the minus alpha x dx, this is going to be given by n factorial by alpha to the n plus 1. If we use this, then this step becomes minus 2h cross square z cube by me into a0 cube. Now if we look at the first integral, of course the integration limit here from 0 to infinity, that is the limit of r1. So the first integral here is going to be minus 2z by a0 into r1 e to the minus 2z r1 by a0 dr1. So according to this formula, therefore we will have minus 2z by a0 will be out of the integral. Integral r1 e to the minus 2z r1 by a0 means we have n equal to 1. So we have factorial 1, and then alpha is 2z by a naught. That means this should be a naught square by 2z whole squared. For the second term, we will have as usual z square by a naught square out of the integral, and then we have r1 square, that means n is equal to 2 e to the minus 2z r1 by a0. That means this integration will give us 2 factorial divided by 2z whole cube and another a0 whole cube. So this is the result of the integration. So now if we simplify, we have minus 2h cross square z cube by me a0 cube. The first term will be minus a0 by 2z, and the second term will be a0 divided by 4z. If I am not mistaken, this is a0 by 4z. Yes. Then this is going to give us minus 2h cross square z cube by me into a0 cube into minus a0 by 4z, which is nothing but h cross square z squared divided by 2 me a0 squared. Now a0, we have written it somewhere. A0 is this object, 4 pi epsilon naught h bar square by me into e squared. So if I simply put this expression for a0 in this expectation value, I replace this a0 square, then what we will obtain is z square, and then we have me e to the power 4 divided by 2 into 4 pi epsilon naught whole square h bar square. What about the expectation value of the potential energy for the first electron. If we evaluate this, that means again we have to evaluate D3R1 psi 0 N1 L1 M1 R1 and then minus Z E squared by 4 pi epsilon naught R1 into psi 0 N1 L1 M1 R1. Again use the same technique, that means you write this as 4 pi R square R1 square d R1 and use the explicit trial wave functions, and final result of this calculation I am mentioning, that is going to be z square e to the 4 me divided by 4 pi epsilon naught whole square h bar square. So this we have expectation value of the kinetic energy and the potential energy for the first electron. The expectation value of the second can also be the expectation value of the second electron, or maybe more precisely of the second term in the Hamiltonian. By second term I mean the Hamiltonian, this term. So second term in the Hamiltonian will contribute the same amount for T2 and V2. Therefore, we can just double the expression that we have obtained for our first electron. So this ground state energy should be the expectation value, total expectation value of the kinetic energy plus the expectation value of the potential energy. Remember, this kinetic energy expectation value was z square me e to the power 4. Now we need to multiply this by 2. So this is 2z square me e to the power 4 divided by 2 into 4 pi epsilon naught whole square h bar square minus this also will be multiplied by 2z square me e to the power 4 divided by 4 pi epsilon naught whole square h bar square. So this therefore leads to an expression which is z square minus 2z square into all the rest of these coefficients are same. So this is going to be minus z square m e to the power 4 divided by 4 pi epsilon naught whole square into h bar square, which we can of course write as minus 2z squared and divide by 2 here. But then this expression is very much familiar to us with a minus sign in front. This is nothing but 2z square times the ground state energy of the hydrogen atom, or to that effect this is nothing but 2z square times the Rydberg. Rydberg was m e to the power 4 in divided by 32 pi square epsilon naught square h bar square, whose value of course is 13.6 electron volt. If you write it in terms of the ground state energy of the hydrogen atom, then it is minus 13.6 electron volts. And for helium, we know that Z is equal to 2, and hence E0 should be equal to 8 times E1. That means 8 times minus 13.6 electron volt, which is nothing but minus 108.8 electron volt. However, we note that the measured value from experiment, measured value of the helium ground state is minus 78.6 electron volt. So, of course, the result that we have obtained here for the ground state of helium, this of course is far away from the observed value of the ground state energy of the helium atom. But of course, to start with, this is not a bad result after all. So therefore, the ground state energy is basically, you remember that the ground state energy is basically the same as the binding energy or ionization energy, and it can be easily measured. That is why people have exact results for the ground state energy of the helium atom. Now, this result, this disparity of results clearly shows that we cannot neglect the mutual repulsion between the electrons. Of course, it plays a significant role to the ground state energy. It is clear from this disparity of minus 108.8 electron volt and minus 78.6 electron volt. This is the calculated value when we have neglected the mutual repulsion term, and this is the observed value minus 78.6. So, as we understand that this mutual repulsion plays a significant part, we have to calculate this effect. So, in order to calculate this effect, first of all, we would basically use, like previous problems, a trial wave function with no angular momentum. Since the ground state has maximum binding, it should be spherically symmetric and there is no angular momentum and in the ground state. Now, we can choose psi 0 NLM as the trial wave function. This is a particularly convenient choice because it is an eigenfunction for most of the Hamiltonian. So let me write this Hamiltonian again. So the Hamiltonian acting on psi 0 R1 R2. Remember what was our psi 0? Psi 0 with which we had started was this one. What we are saying is that we will stick to this eigenfunction or the ground state wave function. We will say that our trial wave function is this one. What was the motivation for this choice? The motivation for this choice will be clear. Let me write down this eigenvalue equation here first. So H psi 0 R1 R2 is equal to, so since we are talking about the helium atom, by neglecting the electron repulsion term, we had just seen that this is the ground state energy that is there. So to this we are saying that we have to add this electron repulsion term, and then we put this psi 0 R1 R2. So let us understand this equation clearly. This 8 times E1 is nothing but the E ground state of helium or hydrogen, E ground state of hydrogen. So, according to this equation, it says that ground state energy of the helium atom, so this is E ground state of helium. Ground state energy of the helium atom is 8 times the ground state energy of the hydrogen atom. So, if I write down the eigenvalue equation for the system now, so far we had solved without this term and we have obtained that the ground state energy is 8 times E1. But now we said that we cannot neglect this electron-electron repulsion term because this 8 times E1 is basically too much further away from the original value or experimental measured value of the helium ground state. So, we want to write down the Hamiltonian equation or the eigenvalue equation in this form that I have written here. Now, in writing this, we have chosen the trial wave function as the one which is psi 0 r1 r2, the same one that we have used when we neglected this VEE term. The reason for choosing this as the trial wave function can be thought of as in the following way, that it looks like a convenient choice because the psi 0 r1 r2 is after all the eigenfunction for most of the Hamiltonian, except this part. Remember, this part 8U1 came from the eigenvalue of the two separate Hamiltonians of the hydrogenic atom. Now, therefore, this equation, whatever we have written, this implies expectation value of H should be 8 times U1 is of course just a number, but this VEE is the operator. So, we have to evaluate the expectation value of this electron-electron repulsive term or repulsive potential in this trial ground state wave function. That is what our task is. Now, you can, if you like, actually interpret this equation as the first order perturbation theory with the perturbative Hamiltonian to be written as VEE. I will come to that discussion later, but for the moment, let us look at how can we evaluate this expectation value. So, for that, let us look at what actually is this VEE. This VEE is E square by 4 pi epsilon naught, and then we have e to the power minus z r1 plus r2 divided by a naught divided by r12, that means r1 minus r2 mod, and then we have d3 r1 d3 r2. And of course, when we had written this wave function already, we also have to put this z cube pi a0 cube whole square. What did we do here in writing this thing? We simply did not do any crazy thing here. What we did is that we had chosen, so this equation actually came from the fact that we have psi 0 star r1 r2 v e psi 0 r1 r2. This is our trial Hamiltonian, sorry, this is our trial wave function, this psi 0 r1 r2. We are evaluating the expectation value of the potential energy operator in this ground state, trial ground state. Now you will say, why there is this z cube by pi a0 cube whole square there? Because what are these psi 0 r1 r2? This psi 0 r1 r2, this is nothing but psi n1 l1 m1 star r1 into psi n2 l2 m2 r2, and VEE is nothing but E square by 4 pi epsilon naught mod r1 minus r2. And then we will again have psi 0, of course there is this 0 here, psi 0 n1 l1 m1 r1, psi 0 n2 l2 m2 r2. Each of these psi's here contributes a factor of z cube by pi a0 cube to the power half. There are 4 such terms, therefore it will be a square here in this expression. So our ultimate goal is to actually evaluate this quantity with this particular integral in mind, but now we are probably going to be in trouble because we are having this double integral here, and we will basically try to integrate this using a particular trick. For that, let us actually think of the picture what we have at our hand. See, we have this axis, say like this, and in this axis we have the position vector which is given by, say, r1, suppose this is r1, and also there is another position vector which signifies the position of the second electron, which is, say, r2, and suppose there is this angle theta in between them, and then this is my r12 vector. Now the trick here is to choose the correct coordinate system, correct orientation for the coordinate system. Now in this particular problem, it is always better to choose your coordinate system in the following way. Let me draw it first, and then I will explain why it is a good choice. So I propose that we have a coordinate system like this, where this is my x2, y2 and z2 coordinate. Let me orient my r1 vector along the z2 direction. So what I am saying is that I will actually orient my r1 vector along the z2 direction. So once I choose the r1 vector along the z2 direction, the r2 vector is somewhere here, and this is going to be my r1 minus r2 mod, and this projection is going to be the phi 2, and this is going to be my theta 2. So basically, in this present choice of coordinate system which I have just drawn here, I had to start with, I had this picture here. Now what I am saying is that the angle theta between these two particles, which is here, is a completely separate thing. We could not have, it's kind of an extra parameter that is entering into the problem. I want to remove this particular angle, and for that I am choosing my r1 vector along the z direction, and I know that for that whatever my r2 will be, because of this particular choice, the angle between them, this r1 and r2, will always be my azimuthal angle or the polar angle theta 2. So now this theta 2 is at my hand for the second particle, theta 2 is for the second particle, and in particular I can also write down this r1 minus r2 mod using the cosine formula. So this is nothing but r1 minus r2 whole square. This is basically r1 square r2 square minus 2 r1 r2 cosine theta 2 square root. So in these coordinates, it is simple to do the integration over the angular variables for the first particle and over phi 2 for the second. So earlier in this particular picture, it would have been extremely difficult to handle all the angular integration, simply because I have to somehow manage this theta, because if I have to write down this r1 minus r2, this angle will always come. Because of this particular choice of coordinate here, our calculation will become little bit more simpler. So how it will become simpler, let us look at it. So this VEE will be E square by 4 pi epsilon naught Z cube by pi A0 cube whole square. So what are the integrals now? Let us write it down. We have dr1 r1 square e to the minus 2z r1 by a0. Then we have dr2 r2 squared e to the minus 2z r2 by a0. And then we have integral. There is a theta integral, and I know that this is basically r1 r2 square sine theta 2 d phi 2 dr2 d theta 2 d phi 2. That is my d cube r2. So d cube r2 was here. That is nothing but r2 square sine theta 2 dr2 d theta 2 d phi 2. That is what d3r2 is. But now there is this r1 minus r2 mod here. So this will become therefore square root r1 square plus r2 square minus 2r1 r2 cos theta 2, and here it will be sine theta 2 d theta 2, and the rest of the things will be d phi 2, and the theta 1 integration will have sine theta 1 d theta 1 d phi 1. So this is going to contribute 2 pi, because there is no phi dependence anywhere, phi 2 dependence anywhere. This is going to contribute 2 pi, and sine theta 1 d theta 1 from 0 to pi is going to contribute 2. So together we will have 8 pi square, and this is from 0 to pi. So I will take out this 8 pi square from these other angular integrations. All this will be taken out of the integral, and we will have 8 pi square e square by 4 pi epsilon naught z cube by pi a0 cube whole square. This will be dr1 into r1 square e to the minus 2z r1 by a0, then dr2 r2 square e to the minus 2z r2 by a0, Now I will use this trick that I will write this whole sine theta 2 d theta 2 as minus of d of cos theta 2, right? So I will write this as d cos theta 2 with a minus sign in front, and this will become square root r1 square plus r2 squared minus 2 r1 r2 cos theta 2 integral. And now because this integration is from 0 to pi, this will be changed to from 1 minus 1 to plus 1. That's it. And here what we will obtain finally is the following. Our pi, 1 pi will get cancelled, and we will have minus 2 pi e square by epsilon naught z cube by pi a0 cube whole square. We still have all these dr1 square e to the minus 2z r1 by a0, dr2 square e to the minus 2z r2 by a0. And I know how to do this integration. This is very easy, because now you just choose your cos theta 2 as say t. Then I have this integral as dt by square root a plus 2t. And that integration is very easy to do. If you do that integration, what you will obtain is the following: into r1 minus r2 whole square minus square root of r1 plus r2 whole square divided by r1 r2. This is what your result will be when you do the integration from minus 1 to plus 1. Now of course there is still some intricacies left in this integration. Firstly, we have minus 2 pi e square by epsilon naught z cube by pi a0 cube whole squared. All these integrals are there. dr2 r2 squared minus 2z r2 by a0, and this particular part will now lead to mod of r1 minus r2 minus mod of r1 plus r2 divided by r1 r2. These modular signs are little bit problematic or little bit odd, but it can be dealt with very easily. Let us do the argument here. Give the argument here. Because see, the argument is the following: the integral is symmetric. Integral is symmetric in r1 and r2, right? There is no doubt about that. The regime r1 greater than r2 must give same result as the regime r1 less than r2. In fact, that means we can then focus on one of these regimes, either this or that, and then multiply by 2. So suppose we look at r1 greater than r2 only. Now if r1 greater than r2, what does r1 minus r2 mod minus r1 plus r2 mod give? This gives us, because r1 is greater than r2, we have just r1 minus r2 minus r1 minus r2. So r1 gets cancelled. We have minus 2r2. And we will just double the result once we have assumed that r1 greater than r2. So what will happen to this integral when we are writing this as r1 greater than r2? So expectation value of VEE, it should be something like this. we had a factor of 2 pi e square by epsilon naught with a minus sign. Then we had z cube by pi a0 cube whole square. Then we said that we are looking at R1 greater than R2, and whatever we will get for R1 greater than R2, we will get the same contribution for the regime R1 less than R2. So we will just multiply the result by 2. Let us do that here. So I multiply by 2. But then there will be another 2 because we are looking at R1 greater than R2, and this part R1 minus R2 minus R1 plus R2 mod is going to give us minus 2 R2. So this minus 2 has to be taken care of. So let us put another 2 here, but then our minus sign also has to be kept. So this is equal to minus this thing. Then the integrations are all very clear. So this is dr1 r1 e to the minus 2z r1 by a0, and then this is dr2 r2 squared e to the minus 2z r2 by a0. What happened here is that there is this r1 into r2 in the denominator. So one r1 get cancelled. Here it was r1 square. So this r1 gets cancelled here. And from this r1 minus r2 minus mod r1 plus r2, we get the result minus 2 r2 in the regime r1 greater than r2. So that r2 gets cancelled here. Only this 2 remains here. What about the limits? Now R2 in principle can run from 0 to infinity. It's radial coordinate. But once R2 runs from 0 to infinity, I know that R1 is greater than R2. So the limit on the R1 integral, it should be actually in principle from R2 to infinity, because R1 is greater than R2. Therefore, I have to first do this R1 integral. So let us do that. So this is equal to, in fact I made a mistake here. There was a minus 2R2 here. So that minus 2R2, and earlier there was a minus sign in front. We will make this plus. So I have 8 pi e square by epsilon naught z cube by pi a0 cube whole square. And then I have to do the integration, this integration, but now I cannot use the formula that I have written earlier. I have written earlier this formula which was used, this formula. This formula now we cannot use anymore. Why? Because the limit has changed. The limit is no longer from 0 to infinity. The limit is now from R2 to infinity. So we have to do this integration by parts. So if you do this integral by performing integration by parts, that part I am sure you will be able to do. Let me write down the final result. So this is the R2 integral, which is from 0 to infinity, and the result for the R1 integral, by putting the two limits, it becomes minus e to the minus 2z R1 by a0 times R1 a0 by 2z plus a0 by 2z whole square. In fact, you need to put the limits R2 to infinity, and then we have the standard R2 integrals, R2 square e to the minus 2z R2 by a0, and then dr2. But then you look at this limit, the upper limit infinity, this whole thing vanishes. This whole thing vanishes because we have e to the minus infinity. The only lower limit will exist. So if the only lower limit exists, the final thing will be 8 pi E0 square, E squared by epsilon naught Z cube by pi A0 cube whole square. And this is going to give us integral 0 to infinity dr2 r2 cube e to the minus 4z r2 by a0 by 2z. What happened is the following. Once I put the limit, lower limit r2, all this becomes minus e to the minus 2z r2 by a naught. This also becomes r2 a naught by 2z. So that's why everything is here like this, a naught by 2z. And once this is e to the minus 2z by into r2 by a0, this gets multiplied with this and finally gives you 4z r2 by a0. Similarly, the second integral will be from 0 to infinity dr2 r2 squared e to the minus 4z r2 by a0 into a0 by 2z whole square. So that's it. Now you can use that particular formula. The formula was x to the n e to the minus alpha x dx integral from 0 to infinity is n factorial by alpha to the power n plus 1. Use this formula and now the final result is very easy to obtain. You can finally obtain if you simplify this. I am not doing this simplification because this is just pure algebra. Please do it, the middle steps. The final result that you will get here is 5 by 8 z e square divided by 4 pi epsilon naught into a0. That is the result that you are supposed to get now. But then again here you put back what is your a0. So this is 5 by 8 z by 4 pi epsilon naught, but a0 is nothing but 4 pi epsilon naught h bar squared. So there will be 4 pi epsilon naught square h bar squared and then me into e square, which is again 5 by 8 z me e to the power 4 divided by 4 pi epsilon naught whole square h bar squared, which is nothing but 5 by 8 into 2z me e to the power 4 by 4 pi epsilon naught whole square into 2 h bar squared. Because this particular object I am using many times, so you must be familiar by now, is the ground state energy of the hydrogen atom, of course with a minus sign. So this will be minus 5 by 4 z into E1. What is this E1? E1 is minus me e to the power 4 by 4 pi epsilon naught whole square 2 h bar square is the ground state energy of hydrogen. So now it's clear. Now you just put for helium z is equal to 2. This implies minus 5 by 4 into 2 into minus 13.6, which is nothing but minus 5 into minus 6.8 electron volts. Let me separate this part, which is nothing but 34 plus 34 electron volts. So what will be my expectation value of H therefore? Expectation value of H, let us go back to this equation. This is my expectation value of H. 8 times U1 plus expectation value of VEE. So I will write it as minus 13.6, U1 is minus 13.6 into 8 plus 34.0 electron volts, which is of course minus 108.8, which was our earlier result, minus 108.8 plus 34 electron volts, which is nothing but minus 74.8 electron volts. Not bad, huh? So we have, instead of basically figuring out using perturbation theory, we have just used the variational technique, where our trial wave function, remember, was the original wave function that we had chosen. So this was our trial wave function. Trial wave function we did not change at all. So whatever trial wave function we had chosen when we have calculated, so this is the trial wave function to start with. This is our trial wave function to start with when we had neglected this VEE, or the electron-electron repulsion term. Then we had introduced the electron-electron repulsion term, and we have actually said that let us stick to this trial wave function only, this psi 0 r1 r2, and let us see what our result is. To our surprise, we figured out that we have obtained a result which is minus 74.8 electron volts. The experimental value, recall, experimental value I have just said in the previous few pages, it's minus 78.6 electron volt. So of course, if you compare these two, this minus 74.8 electron volts is far better than minus 108.8 electron volts, which we have obtained by neglecting the electron-electron interaction term. After we incorporated the electron-electron interaction term, our result has improved much further, and we have come very close to minus 78.6 electron volt. However, of course, this shows that there is still scope for improvement, and that we will be discussing in the next class.